Hi, welcome to another MDE paper of the week. Paper that I chose for today is Features as Transformations, a generative approach to software development. This paper has not really taken the world by storm. It's a 2016 paper and there's only one citation, so it's not exactly the most popular paper in the world. But I was very curious as to what they want to talk about here because, Features as Transformation sounds quite an appellative sort of title. It's a very long paper, maybe that's one of the reasons why it hasn't taken the world on storm, 20 pages. We might have to skip a little bit, but we will try our best to parse it as much as possible. So without further ado, let's get cracking. Abstract. The objective of feature modeling is to foster software reuse by enabling to explicitly and abstractly express commonality and variability in the domain. Okay. Feature modeling is used to configure other models and eventually code. The software assets are being configured by the feature model based on the selection of variable features. However, selecting a feature is far from a naive component-based approach where feature inclusion would simply mean including the corresponding components. More often than not, feature selection affects several places in models or code to be configured, requiring their non-trivial adaptation. So this is really the crux of the problem, really. Let's start highlighting, I think. This is the problem that everyone sooner or later faces. Thus, feature inclusion recalls transformation, and this is at the heart of the approach to feature model-driven generation of software artifacts proposed in this paper. Features are viewed as transformations that may be executed during the generative process conducted by the feature model configuration. The generative process is distributed in respective transformations, enabling the developers to have a better control over it. Okay. This approach can be applied to modularize changes in product customization and to establish generative software product lines by gradual refactoring of existing products. Okay, so what should we highlight here? Perhaps this bit. So we have a red here, which is the problem. Try a couple of goes as usual. And the green here, which is how they intend to solve the problem. This approach can be applied to model. Okay, we read this bit already. So introduction. Feature modeling is a widely known approach to capturing commonality and variability proposed in the 1990s. Although industrial applications of its academic form, not counting in some cases of using the pure variance notation and tool, are unknown. It is widely recognized that commonality and variability lie at the heart of organizing software development for reuse in software product lines. Based on commonality and variability, appropriate implementation mechanisms can be selected. I think, okay, it's very good points, but I'm not entirely sure we're going to get out of there. Feature modeling is used to configure other models and eventually codes. The software assets are being configured by the feature model based on the selection of variable features. However, selecting a feature is far from a naive component-based approach where feature inclusion would simply mean including the corresponding component. To be honest, that's kind of what we're trying to get at with Dogen. Perhaps a note here. Feature selection. Authors claim that feature selection is a much more complex process than merely enabling a component. We are striving to make it so. More often than not, a feature inclusion affects several places in models or code that belong to other features requiring non-trivial adaptation, or to use a more appropriate word, their transformation. This is known as feature interaction. So there's another challenge. Previous notes. The fact that features interfere with each other and may require adaptation in order for the system, or for the in order to be applied to the system, something like this. In his keynote at Modularity 2016, Sven Appel admitted that only after years of fighting he found feature interaction is inevitable and actually necessary. By perceiving features as transformations, resolving feature interaction becomes their intrinsic part rather than something that has to be tackled externally. Okay. This is going to be a very highlighting paper. Modularizing other models and code by features has been recognized as a viable approach to implementing features in some of the so-called language-based approaches, such as GenVoca or AHEAD. So we've seen GenVoca already, we haven't seen AHEAD yet, that fall into the category of feature-oriented programming. However, such approaches require language extensions which are hard to keep compatible with the ever-changing host language without dedicated support. Another way to see feature interaction is cross-cutting in the sense of aspect-oriented programming, but aspect-oriented programming extensions that are stable and up-to-date with the host language are not available for most programming languages. On the other hand, cross-cutting features have been reported to have been perceived as problematic by developers. This is the key problem. Yet a significant number of features exhibit a cross-cutting nature, and such features are often highly important. And so I'm afraid we're going to end up highlighting half of this paper because so many interesting points. The approach to feature model-driven generation of software artifacts proposed in this paper is intended to overcome the problems mentioned above. It does so by providing a self-contained transformation framework realizable in a general-purpose object-oriented programming language capable of making model-aware interventions and handling cross-cutting features by modifying the transformations that implement other features. The generative process is distributed in respective transformations, enabling the developers to have practically unlimited control over it, given by the power of the general-purpose programming language being used. At the same time, the developers have to implement and maintain only that much of the generative process that is really necessary. So there's a lot of claims here. I mean, almost worthwhile highlighting the whole thing. Seems extremely promising. Very large, bold claims. The rest of this paper is organized as follows. Section 2 offers a view on features as means for software modularization. Section 3 explains how features can be perceived as transformations, with the essence of the approach proposed in this paper, which is the essence of the approach proposed in this paper. Section 4 presents the implementation of the approach in the form of a framework. Section 5 demonstrates the application of the approach. Section 6 discusses how the approach can be applied in software product customization, viewing changes as transformations, and how this can be extended to software product lines. Section 7 discusses related work. Section 8 concludes the paper. So, on to modularizing software by features. While there is no perfect software modularization, and ultimately any kind of modularization is condemned to tyrannize some developers or other stakeholders, features are a particularly interesting form of software modularization from the perspective of the application domain. Simply stated, a feature is an important property of a given concept, and any concept itself can be perceived as a feature of another concept. So yet again, sort of very difficult to pin down kind of definitions. Roughly speaking, features imply from requirements and domain analysis, but feature modeling actually does not deal with features themselves but their relationships. These may be captured graphically by feature diagrams. In feature diagrams, features are usually organized hierarchically into trees, being easier for humans to follow trees than general graphs. Features are usually organized into hierarchies of trees, while additional relationships are expressed textually. Figure 1 shows an example feature diagram for Zarnecki-Eisennecker notation. Edges and arc decorations denote the kind of feature variability. So this is just basically standard feature model, so we're just going to skip through this quickly. A filled circle ended edges that stand for mandatory features, an empty circle ended edges stand for optional features, and groups alternative features. A feature diagram defines a whole family of products and product parts. Each member of a family is defined by a configuration of the features. Figure 2 shows several valid configurations of the simple website, including the minimal one, with only one feature besides the root one. Depending on its variability constraints, a feature may or may not be included in a configuration. A feature may not be included in a configuration if its parent feature is not included. So here we have a simple website with a contact page, static content history, dynamic content access log, and so this is kind of modeling the different features of the website. Feature modeling can be used to configure software assets, models and code, in order to create software instances that exhibit the desired features. One way to achieve this is by employing the so-called superimposed variants, where the software models or code contain all the variants that are being reduced based on the feature selected or not selected in the corresponding feature model. The Feature Warehouse project implements an approach that uses these models and allows language-independent source code generation. Right, so this is basically just a superimposed variants method, which is already known from the literature. It's quite annoying. Delete. Oh. It's quite annoying how the highlights always seem to be a bit too big. Let's try again. Where were we? Slightly lost. So we were just looking at features. Features transformations. I think we've moved too far now. Here. Right, here we are. So, what we're meaning to do is to highlight this bit here and to change it to green. Right, now then. The opposite way is to generate or add pre-built software artifacts according to the features contained in a software configuration. The Pure Variance software tool uses a specialized family model to represent a feature to architecture mapping. In this model, it is necessary to specify the type of the impact on the software instance. There are several possible impact specifications that allow for a wide scope of software artifact to be created, such as files, file fragments, XSLT transformations, conditional XML or text, C++ flag files, make files, class alias or symbolic links to folders and files. Okay. This also seems quite an interesting point. Features can represent anything, so it's interesting that it didn't really go very far from here. So the two ways we got here then. One way is superimposed variants. The second way is pre-built software artifacts. Okay. Features can represent anything. At some point, one may be tempted to use them to extensively model structural concerns. The logical next step would then be to extend feature modeling with multiplicities, cardinalities, and this has actually happened. So what is 13? For such a large paper, scrolling is not a good idea. Okay, just a Zarnecki paper. We probably have bumped into it before. However, the original perception of features is different. A feature is like a proposition, and to include a feature several times would simply mean to state the same thing several times. This keeps feature models focused on the configurability aspect, and it is in accordance with viewing features as transformations. While transformations in general may be repeatable and their repetition may even make sense, that would unnecessarily complicate the whole model. The same effect may be achieved by transforming transformation parameters, one of which may be the number of times to repeat the transformation. So, features as transformations. Generating software artifacts independently for each included feature may be sufficient only for simple situations. In reality, features may interact, and this interaction may result in the necessity to generate different software artifacts for the affected features or to change them if they are already generated. But changing already built things may require deep restructuring. To compare more tangible artifacts, once a sculpture... okay, right, so before we go any further, this seems important. To compare more tangible artifacts, once a sculpture is cast, it's very hard to modify without making this obvious. A smoothly modified instance of the sculpture can be obtained only by modifying the cast itself. Similarly, instead of modifying generated software artifacts in order to get a smooth result, it is more appropriate to modify the procedure that generated them. Those procedures actually transform the pre-manufactured software material into its final form. If each feature is viewed as a transformation, this can be taken one step further. Okay, I quite like this notion. If each feature is viewed as a transformation, this can be taken one step further. The transformation associated with the affecting feature could modify the transformations associated with the affected features instead of harshly modifying already generated software artifacts. Although transformations still will mainly have to result in generated functional code, a transformation can represent virtually any kind of action, including those that reflect extra functional requirements. Thus, it is legitimate to have a transformation that will provide logging or documentation. This section explains the overall process of our approach to feature model-driven generation of software artifacts based on features as transformations and its different aspects. So the overall process then. The overall process of the approach to feature model-driven generation of software artifacts based on features as transformations is depicted in figure 3. The whole process actually consists of two processes, one of which is the transformation design and the other one is their application. This is analogous to distinguishing domain engineering from application engineering. Okay. So, transformation design, feature model and other domain knowledge, determine the transformations, implementing the transformations and assign them to the features, determine the order of transformation execution, feature model with assigned transformations. Transformation application, customer needs, configure the feature model, provide transformation parameters, execute the transformations, produce code and other generated artifacts. Okay. It's in some ways similar to our approach, I guess. The input to the transformation design process is a feature model and other domain knowledge. This process embraces determining the transformations that are necessary, implementing these transformations and assigning them to the corresponding features, and determining the order in which transformations are to be executed. Although not indicated in figure 3, the process is iterative and incremental. The process of the transformation application starts with customer needs, which determine what features are to be included in the corresponding feature model configuration. In turn, the selection of the features determines the set of transformations to be executed. The corresponding parameters are provided to the transformations, and finally, the transformations are executed to obtain the product code and other generated artifacts such as documentation. Again, this process is also iterative and incremental, requiring to experiment with the selection of features that suits best the customer needs. This embraces experimenting with transformation parameters too. More often, the need of changes may also propagate into the transformation design process and even affect the feature model itself. Experimenting with transformation application is also of particular importance in ensuring the order of their application is correct. We use the term extra-functional, as proposed by Mary Shaw, to refer to requirements and features that go beyond the software system functionality, instead of more widely used but potentially confusing term non-functional. Okay. Method transformations. Some features may have a global effect that spans through the whole software product or its significant parts. Quality features such as logging, actually let's go check how are we doing for time. Not too bad. Some features may have a global effect that spans throughout the whole software project or its significant parts. Quality features such as logging requirements of performance and security constraints represent a typical example. Other features rooted in extra functional requirements often have an effect too. Including such a feature with the corresponding transformation into the configuration leads to the necessity of accessing or modifying the transformation parameters or actions. I mean, you can already start to see the complexity of trying to do an approach where we allow features to interfere with each other. It is clearly very, very complicated. We denote the transformations capable of this as meta-transformations. They correspond to the concept of higher order transformation, and in particular to two kinds of higher order transformations: transformation modification with respect to modifying transformation actions or parameters, and transformation analysis with respect to accessing transformation actions or parameters. The notion is also related to the concept of model transformations. So, associating transformations with features. One way of associating transformations with features with transformations is to include the transformations directly in the feature model. There are two main problems connected with this approach. The degree of the transformation reuse between different models is reduced, and it is necessary to parse the transformation information separately for every feature, even though the type of the transformation they use may be the same, e.g. create a file. Another approach is to store the transformation definitions outside the feature model, as demonstrated by this C# class. Create file, transformation, execute transformation. A feature model then includes only the association itself. Feature, transformation, class name, create file. Although a feature appears to be associated with the transformation class as such, it is rather its instance it is associated with. This way, in addition to the actions to be performed within the transformation, common to all instances, each such transformation instance can have its own independent state to operate upon. This state will usually depend on the transformation parameters, such as file or folder naming in the creating folder, in the creating a file or folder transformation. Whilst what transformations are to be executed is given by the selection of features in the feature model configuration. It is obvious that the order of execution is significant. The order may be defined externally, i.e. globally for the whole feature model, or internally, locally for each feature. Okay. An internally defined order, where each feature defines what other features have priority over it, overcomes the necessity of a global rearrangement of the feature order upon a change in the feature model, which is unavailable with the externally defined order. Transformation granularity and modularization. Besides the features used merely to group other features under a common denominator, which might have no corresponding transformations, such as dynamic access log in our family of simple websites we call figure 1, and any other feature would normally be associated with a transformation. This is in accordance with the separation of concerns principle, but may lead separation of concerns principle is interesting here, but may lead to concern fragmentation, which may cause difficulties in concern comprehension. To avoid this, a general concern may be captured in one transformation modified by the meta-transformation assigned to a variable features depending on their selection in the feature model configuration process. See if we can get our highlighting right for once. An extreme of this would be having only one general transformation presumably associated with a root feature. On the other side, the transformation associated with one feature may actually comprise several transformations that in turn may be individually associated with other features. This is extremely complicated. In general, such a composite transformation may invoke the transformations it comprises within its course of actions and conditionally or repetitively. These transformations can be composite themselves. Transformation reusability. The process of the transformation design requires interaction on part of a domain engineer to provide the necessary domain information specific to the project and software engineer and a software engineer to design the transformation in such a way that they implement the transformation. They implement the information provided by the domain engineer and the requirement analysis of the corresponding features. So this is the usual pairing that you need of a person that's doing the requirements capture and the person that's actually implementing the transformation, right? For an effective cooperation between the domain and software engineer, it is useful to distinguish usability levels of transformations. So specialized transformations that can only be used for the specific features in a specific configuration of the feature model. Specialized transformations that can be used only for the specific features but any configuration in the feature model. Domain-dependent generic transformations which can be used across multiple software product lines in the same domain. Domain-independent transformations which are the most reusable transformations as they can be included in different software product lines across multiple domains. So we should probably state here classification of transforms. Authors provide a simple classification of transforms which can be used also to describe disrupts in Dogen. So in other words, the patterns that we're trying to obtain and classify in Dogen are very similar to these transformations, and the principles that he talks about here are also the principles we need to obey. We just have a slightly different approach in how we get there. But the general idea is that when you capture a pattern, that pattern then has certain reusability, and this is what the authors sort of talk about here. As with common object-oriented programming, inheritance can be used to realize some aspects of transformation reuse. In this, actions play the role of methods, and a device transformation can preserve the inherited actions, add new ones, remove some of them, or override them. So clearly you can't remove an inheritance, but that's fine. The inheritance model can also be perceived as a way of organizing transformations into logical groups or packages. With respect to this, the inheritance is purely a tool of categorization and is not necessary to maintain a typical parent-child relationship, i.e., if transformations are represented as classes, it is not necessary to support inheritance mechanism at the level of methods and attributes. Okay, so basically inheritance is just a mental model that we're using here. The framework. We implemented the proposed approach to feature model-driven generation of software artifacts based on features as transformations as a framework in .NET using C#. The approach itself is by no means limited to .NET, also can be implemented using other object-oriented programming languages. The overall architecture is depicted in figure 4. The details that are explained in section 4.1 to 4.5. So we have some kind of interface for the feature model parser, execute transforms, parse meta transformations. Let's have a quick look at the description. All transformations in our implementation are objects of the transformation class that implements the iTransformation interface. The check prerequisites method performs some basic parameter checking before the transformation is processed. In general, it is possible to provide the model-aware method at the level of a meta transformation that can check the transformation dependencies too. The execute transformation method represents the action which is contained within the transformation. This method is called in the final step of model processing. The get parameter names method is used in the XML file parsing to provide the parameter names to be retrieved from the feature node attributes. The get meta transformations method provides a way to retrieve the meta transformations that are connected with this transformation. This allows to connect the meta transformation list with the transformation, and by this provide it with model awareness, which means it can influence other transformations in the model within the possibilities provided by the connected meta transformations. The parameters are stored in the dictionary format in the parameters attribute. I mean, we're not really going to spend too much time understanding the ins and outs of this, but so a quick parse. A composite transformation contains an object of the transformation store class, which is basically an ordered list of transformations. For processing these transformations, the check prerequisites and execute transformation methods have to be overridden. The contains transformations are instantiated by overriding the instantiate chain method. This method is automatically executed by the transformation store object when adding transformation to it during parsing. The contained transformations may themselves be composite. That is obvious from the implementation, since transformations are processed recursively in a depth-first order. The method transformations are implemented by the method transformations class. The difference between this class and the transformations class is that the method transformations class is model aware. This means that it can traverse the feature model and make changes to it. For this, they execute transformation methods that takes an argument all transformations within the transformation store object. To allow for the mitification of composite transformations, this method is implemented in a recursive way. Feature model configuration. In our implementation, feature model configurations are represented by XML files. The structure of these files follows the tree structure of the feature diagram. So here is a feature model with features and recursion. Each feature model node has 3 compulsory attributes: a name, an ID, and a transformation. Accordingly, the simplest feature node looks like this. Feature name, dynamic content provider, ID 7, transformations are empty. The name and ID attributes have solely the purpose of identifying the node when it is being processed. The transformation attribute specifies the transformation that will be used with this feature. The transformation attribute consists of 2 parts delimited by a comma. The first part represents the dynamic link library that contains the transformation, and the second part, the full class name of the transformation. The dynamic link library has to be a .NET managed library. Therefore, a field transformation attribute looks like this example. Transformation org.crdp.dp case study simple web final transformations are empty. The XML feature model configuration is afterwards transformed into an object model contained with the transformation store objects. Parsing and executing transforms. So this is all going to be quite straightforward, presumably. The generative process consists of these steps. Parse the feature model configuration from the XML file. Parse and execute the method transformations contained within the transformation from the XML file. Check the parameters of the parse transformations. Execute the transformations. The step of checking the parameters before parsing. The method transformation is omitted as it is contained within the method transformation parsing step. The actual generation of code and other artifacts is performed by the transformations, making the whole generative process distributed. An abstract description of these steps is provided in the form of an interface denoted as iFeatureModelParser. As it has been mentioned in section 4.4 in our implementation, feature model configurations are represented by XML files. Therefore, we implemented the corresponding XML parser and transform executor as the XML model parser class. We refer to it simply as a parser in the following text. The first step that is necessary is to translate the transformations from the XML feature model configuration into an object model. The transformations are parsed in a top-down order. It is possible to override this behavior using the priority attribute at transformation nodes. First, the assembly and class name are parsed in the XML nodes, and the transformation instance is created using reflection. Probably not the most performant of processes, but so as you can imagine, what's happening here is that we are basically using reflection to load assemblies on demand and obtain the transforms as mentioned in the XML file. Afterwards, the getParserNames method is used to obtain the list of parameters that this transformation uses, and the XML node attributes that correspond to this list are copied into the dictionary containing the parameter key value pairs. The transformations are stored in a list implemented by the transformation store class. Its addTransformation method allows for priority-based insertion of transformations. The transformation type is preserved in order to enable distinguishing composite transformations during their execution. The isSubclass of class method uses .NET Reflection to recursively check for a match in all ancestor classes up to the object class. Reaching the object class signals that we are at the top of the hierarchy, as in the .NET, the object class is the topmost class from which all classes implicitly inherit. This step ends by adding all the transformation objects to the store, by which they become part of the object model, making the XML model unnecessary. So we just basically bootstrapped the object model from the XML, and now we got all the transforms in a nice little order. After adding the transformations in the transformation store, it is possible to perform method transformations over this object model. The method transformations are separated from all transformations, preserving their order as in the transformation store. After obtaining a complete method transformation store, it is possible to proceed with checking the prerequisites and perform the execution of method transformations. Afterward, the changes to the transformations contained in the process method transformations have been applied to the transformation object model, and therefore it is possible to perform the final prerequisite check over the model and proceed with the executing the transforms. To check their parameters, the check prerequisites method is executed for each transformation in the transformation store object. The current implementation uses a simple fault detection mechanism that is based on raising an exception when a problem occurs. With method transformations, it's also possible to check for transformation dependencies using the enhanced model-aware check prerequisites method with the necessary parameters. To execute transformations, the transformation store object has to contain a list of transformations that is prepared in a way that the method transformations have been applied and the prerequisites checked. Afterwards, the execute transformation method is called in a loop for each of the transformations contained in the list. So we just basically traversing the graph, calling execute transform. In the order in which the transformations are executed is defined by their order in the transformation store object. The execution finally creates the corresponding software artifacts. Okay, so applying the approach. See what we're doing for time. Not too bad. So to demonstrate its applicability, we'll use. So again, we're just going to skim through this a little bit. We're more interested in the final conclusions at the end. To demonstrate its applicability, we use the framework for feature model-driven generation of software artifacts based on features as transformations described in the previous section to develop a family of simple websites as presented in section 5.1. We also applied the ideas behind the approach in practice described in section 5.2. The discussion is provided in section 5.3. Using the framework, the feature diagram of the family of simple websites has been introduced in Figure 1. Variability includes having static content history, dynamic content access log, microformat support, custom HTML header, and generated documentation. The actual content is provided by transformation parameters. Consider the create static HTML page transform as an example. This transformation embraces a prototype HTML file and its HTML content attributes. So this looks very much like a template of some kind. This transformation has 4 parameters used to adjust the prototype HTML file. Page name, the file name under which, so basically page name, HTML template, HTML title, HTML content, and so these are basically the parameters we're going to use to parameterize our template. If the corresponding feature to which this transformation is associated is included in the feature model with the following parameter configuration. So presumably we're just going to supply the parameters, as you can imagine, HTML content, HTML title, and so forth. The following HTML file will be created, and we're just instantiating the template. These page features, contact page, static content history, dynamic content access log, embrace 2 ways of creating the text content. Statically by an HTML document, as with the contact page and static content history features, or dynamically by a script that generates HTML document, as with the dynamic content access log feature. Static content history feature is implemented as a composite transformation. A model-aware transformation is included with the dynamic page feature, i.e. the dynamic content access log feature, with the utilization of a meta transformation providing model transversal. Variability is introduced with the data provider, i.e. the dynamic content provider feature, providing an XML or Microsoft SQL database backend. The optional features connect to the root feature, microformat support, custom HTML header, and generate documentation, represent cross-cutting features. They affect other features that are not directly connected with them. The transformations for such features either have to comprise the meta transformations to change the respective transformations, that is, with microformat support and custom HTML features, or they can appear as parameters to influence these transformations, such as the generic documentation feature. Applying the approach in practice. We apply the ideas of this approach to feature model-driven generation of software artifacts based on features as transformations in practice in 3 industrial projects. The application was partial and emergent. Okay, this is a bit more interesting. It concerns security management in one project and partially in 2 other projects in ASP.NET, emerging out of the needs for reuse. Although no explicit feature model was created during the application itself, a featural decomposition was applied, and also no dedicated framework was used, so the transformations implemented in T-SQL and XSLT were executed manually. Figure 5 shows a reconstructed figure model. It abstracts some platform-specific features and corresponding transformations such as modifications of the Visual Studio solution and project files. So here we are, another feature model showing us what's available. Security management is a top-level feature that represents the whole subsystem. It implements a transformation that collects the T-SQL feature scripts, deploys them to the database, and generates the ORM layer. User management represents the management of the user and password store. No transformation is associated directly with this feature, but there are transformations which actually, as I'm reading this, I'm thinking, so what they've done is similar to what we've done, in the sense that we are pushing our features towards a so the feature model and our representation of facets are isomorphic in a way. So we need to make sure we explain this quite clearly, really. User management represents the management of user and password store. No transformation is associated directly with this feature. There are transformations associated with these sub-features. User store represents data store for user records. This feature could be extended by allowing for more types of data stores. Currently, there's only T-SQL is used. The transformation that generates the create table script for the user store is associated with it. I must say there's quite a lot of detail here, and perhaps not entirely necessary for you to get the gist of the approach. They probably should have published two papers, one detailing the approach and the other on the implementation. The transformation that generates a create table script for the user store is associated with it. Extended properties is an optional feature that stands for the addition of custom properties for user records. A composite transformation that consists of 3 transformations that create scripts for regulating custom properties is associated with it. Security model stands for what its name says. No transformation is associated directly with this feature, but a composite transformation is associated with each of these sub-features. These composite transformations follow a common pattern consisting of 3 transformations to generate the scripts that create the corresponding database tables. Thus, the permissions feature regulates user permissions. Roles covers the addition of roles to manage permissions, and organizational unit manages the relation of users to organizational units. In addition, the meta transformation altering the transformation associated with the user store to add the role column is associated with the roles feature. Application security controls in which way the user is authenticated. Composite transformations that copy files and the templates are associated with it. User session support is only a container feature that allows to choose a session provider based on its optional sub-features. With inproc, no action is performed, the default provider, while with SQL and Redis, they activate the meta transformations that alter the files copied in the application security feature transformation. Okay, so what are we doing for time? Getting close to the end of our allotted time, so we may have to skip a bit, I'm afraid. So the 2 example applications presented in the previous 2 sections demonstrated the approach applicability. With respect to reusability, since a website family example comprises only one feature model, by the means of implementation we actually proved achieving only one level of specialized transforms. This can be used for the specific features, but in any configuration of the feature model. However, several transformations, such as those associated with database backend or generative documentation, are potentially domain-dependent generic transformations or even domain-independent generic transformations. We go beyond this with the security management example. The whole set of transformations associated with it is actually at the domain-dependent generic level, proven by their use in 3 projects. The validity of these claims is on one side threatened by the small extent, yes, this is the problem. The validity of these claims is in one side threatened by the small extent of the website family example, while on the other hand, the security managed example comprises no supporting framework with transformations being executed manually. However, the 2 applications are complementary, with each one targeting what is weak in the other one. Also, it is important to note that both examples embrace the application of all 3 kinds of transformations: general transformations, composite transformations, and meta. So they effectively exercise that framework. Now then, changes the transformations. So far, we assumed an exclusive application of the approach to feature model-driven generation of software artifacts based on features as transformations. However, it is also possible to apply this approach to non-exclusively and non-primarily using an existing code base, which in general would not be modularized by features. Okay, I'm going to skip this section because I think this is going to take us a bit too far. Let's have a quick look at the related work. In this section, we attempt to put our approach to feature model-driven generation of software artifacts based on features transformations in the context of related work. We have identified several approaches that address similar issues or appear to be complementary to our approach. Okay, pure variance, as we already mentioned. The pure variance approach mentioned in section 2 embraces a large set of predefined transformations that are assigned to individual features in the family model. The difference lies in their implementation. Pure variance relies on XML transformation definitions, and the solution proposed here uses C# classes. While XML is only markup language, C# is a fully fledged programming language that allows for the transformations to gain full control over the target. The approach itself is not bound to C#. Other programming languages can be used instead. Edicts is another approach that aims at mapping of features to source code parts. In addition, edicts supports variable binding times, allowing for optimal solutions for different contexts. In general, early binding times are more time efficient, while later binding times offer greater flexibility up to runtime feature selection. In our approach, this concern could be addressed by meta transformations. Zana strives for bringing closer the developer process to end users using feature modeling. It decouples software product line design implementation, which is to be performed by more technically knowledgeable users or professional developers, from application derivation, which is intended to be, this is a classic domain engineering approach, isn't it? Which is intended to be manageable by non-technical end users. Application derivation assumes not merely feature selection, but also providing parameters for parameterized features. A similar kind of decoupling could be applied in our approach. Generic transformations could be provided as a framework, while being accompanied by an appropriate development environment extensions to make them accessible to end users for selection. The superimposed variance approach provides a generic way of mapping features to variabilities in external models, which can be used to activate or deactivate particular parts of the superimposed architectural framework. Our transformation-based approach is related to the idea of superimposed variance with respect to the external system of transformations used as the superimposed architectural or model. Differently than in our approach, the superimposed variance approach uses external models that are being configured. An analogy in our approach would be to create search transformations that would prepare and configure additional models. One of the actions that is realized by meta transformations in our approach is parameter replacement. This is similar to the template text replacement based on generic methods in generative programming for C and C++. Moreover, in our approach, a transformation can represent a complex set of actions and not just a simple text replacement. Dynamic code structuring is based on explicit representation of possibly overlapping concerns in code for providing different perspectives, which can help in preserving intent comprehensibility. In our approach, dynamic code restructuring can be applied to codes that defines transformations. However, dynamic structuring is potentially applicable to feature models themselves. In essence, featural software decomposition is a decomposition by concerns, with features representing concerns, including the cross-cutting ones. Feature models with different organizational features in feature diagrams can be equivalent. Moreover, a feature can have alternative decomposition into sub-features, including not being decomposed at all. Different representations of the same feature model may suit different stakeholders or situations, and the transformation code attached to it can be presented in different ways accordingly. Our approach employs the basic Zarnecki-Eisenhower notation, but is not limited to it. Feature models can be represented as grammars, in which case grammar refactoring could be applied to obtain different views. For dealing with large feature models, design pattern detection techniques may be of interest. Conclusions and challenges. This paper proposes an approach to feature model-driven generation of software artifacts in which feature diffuses solution space transformations that may be executed during the generative process conducted by the feature model configuration. This is the important part. The approach was implemented as a framework in .NET. Two examples of the approach were presented, one of which constitutes a practical application. The main advantages of this approach are that the transformation framework is basically self-contained and does not require additional modeling techniques except for the enhanced feature model. The code within the transformation is unlimited with respect to its effects on the resulting software system behavior, i.e., anything that can be achieved by manual code writing can be achieved by appropriate transformations. In large part, the flexibility of the proposed approach lies in the concept of meta transformation. Meta transformations transfer the impact of cross-cutting features. So this is a bit that matters really. Meta transformations transfer the impact of cross-cutting features to the implementation level and modifying the transformations associated with the features being cross-cut before they are executed by changing the input parameters and modifying their actions. There are several research challenges with respect to having features implemented as transformations. A practical adoption of the approach could be significantly supported by providing directly reusable transformations, transformation templates, parameterized transformations, or even just transformation schemes or examples to be adapted manually to the application context. It should be explored further how the approach should be utilized in establishing software product lines out of existing products. With respect to this, implementing use cases as transformations could be an interesting research direction. In particular, this could be related to extension use cases which exhibit a cross-cutting nature. Actual feature models are huge and therefore are more effectively presented by individual concepts. In general, a concept is an understanding of a class or category of elements in a domain. Syntactically, in feature modeling, the root node of a feature diagram represents a concept. Thus, raising a feature to the level of concept is a matter of choice. Having a feature model decomposed into a set of feature diagrams involves maintaining the references between these diagrams. It is necessary to explore how this affects feature model-driven generation of software artifacts. Okay, this was a bit of a whirlwind read of this paper. It's a very long paper, which unfortunately doesn't really help, and we are running out of time. I think this is an extremely interesting paper, and I think we're going to have to perhaps do several parsers of this paper. Clearly, there's a lot of commonalities between their approach and our approach. We just tackle things in a different way. And also, there's the other problem that we always have with model-driven engineering is the problem of terminology. I actually think that when they start to mention features as transformations, I mean, it's confusing slightly because one has to remember that the domain model that you're using will, to some extent, also represent features. So if you take Dogen as an example, if we take a domain model in Dogen, our elements, the elements that we're modeling, they model aspects of the domain, but they are themselves also, in a way, it can be visualized as a feature, because they are modeling featural aspects of the domain. So for instance, determining whether you're using ODB as your relational database management system, well, that's an option, right? And the enablement of things within the domain model will control, to some extent, how features are being generated. On the other hand, we also have, of course, our multidimensional approach to modeling, which somehow links up a little bit to their notion of a feature meta model. We just need to have a lot of clarity how exactly these two concepts are related. But this paper is definitely very interesting. It's a shame that it hasn't been more widely reviewed and cited. We'll definitely be citing it. Okay, I think that's all for today.